Hi everyone. My name is Chen. I'm from Uber Rider Experience, and my co-speaker is Xian from UberEats. So, um, do you unmute me? Okay. Cool. Thanks. Is it better now? Okay, good. Hi, thanks for coming, everyone. My name is Chen. I'm from Uber Rider Experience, and my co-speaker is Xing. He's from UberEats. Today, we're going to talk about how AI power UberEats and how Spark actually power AI platform at UberEats. Okay, before we start the talk, just a quick show of the hands. How many of you guys heard UberEats or used UberEats here? Pretty good. Okay, cool. I hope at the end of this talk, everyone will use UberEats as their first choice. Okay, so as many of you know, Uber basically is a ride-sharing business. But besides of that, we actually have an organization called Uber Everything. It runs similar to Y Combinator, so it curates a lot, incubates a lot of like creative ideas. Uber Eats basically is one of those ideas. So in 2015, December, we launched the Uber Eats as a separate apps in the App Store. You can download it, and it first launched in Toronto. So 3 months later, it expanded to 4 more US major cities. They are Los Angeles, Houston, Chicago, and our home city, San Francisco. So as of today, Uber Eats has been serving almost like 100 cities over 6 continents and 28 countries. Okay, so these charts give you the growth trajectory of the Uber Eats within and the other major market players within last year. And as you see, Uber Eats basically is the top chart here, and without no brainer, and everyone knows who's the market winner here. Okay, so the remaining talk actually has 2 major parts. The first part, I'm going to talk about AI platform at Uber Eats, and my coworker, Chen, he will talk about the AI challenges at Uber Eats. So the AI platform, the major goal here is basically to enable engineers and data scientists to build and deploy their platform and their models at scale. So the typical life cycles goes like this. So you start frame your problems and the models, and then you get your data and training your models offline, and then you analyze your models' accuracies and compare with your baseline models or your current existing models. Your baseline models can be just like a random guess, okay? If you improve anything, you can deploy and shadow your models in the production. And then you launch some monitor process to actually verify your results. So after a few days, you may think, okay, maybe I should add more signals, and then you reframe your problems and models to incorporate these new features and restart this whole process again. So the idea basically is to support all these steps and streamline these steps in a very genetic platform so that we can leverage our Uber Eats data framework, the data infra, and also the microservice ecosystem in-house. Okay, to give you more ideas about this AI platform, so let's use this simple example of building batch models. So the batch models here, what I mean is basically run your models in an ad hoc manner, or you can just run it every day. So the main point is the latency here is not important. So let's see. Okay, so without loss of generality, let's assume our data is basically cleaned, stored, and tabulated in a Hive table. And all you can need to do basically is write some SQL statement, and this statement will spawn off Spark jobs to extract the features and the target levels from these Hive tables. And once you get these features and the labels, you can start training your algorithms and get a trained model. Okay. So this platform actually was used by a lot of platform teams and to build multiple different models. Most of them models may share some feature sets, so we don't want actually to recalculate this feature set over and over again. So the basic idea basically is trying to abstract this feature set in some common or global feature store. Here we can basically use scheduled Spark jobs or ETL to periodically curate and populate this feature set into Hive feature stores and leverage this, and all these feature, global feature set can be shared with all the different teams within Uber. Okay, once we have trained the model, the next thing we can do basically is to launch another Spark job and deploy the models and make a prediction. And you can also pipe the prediction results to the Kafka topic. And this Kafka topic will later on land in a Hive table for the later analysis. Okay. So to close the loop, last but not the least, we basically need to actually have another Spark job called monitor job to verify your model actually is working in the production. And then you can compare the target label with your prediction result and see what's the confidence of your model is. Okay. Oh. So currently, we just covered how to build the batched models, but in reality, we actually maybe want to make a real-time prediction. So for instance, I'm the UberEats user. I open the app, and the app should return the real-time ranking results based on my own preference. So how are we going to achieve this? So one way we can do basically is deploy the model in a real-time service. However, if we have tens or hundreds other real-time services, this solution will not be scalable. So the better practice is to create a centralized real-time prediction service. And this prediction service will take responsibility of managing and serving the model for you. And all the real-time service need to do basically is send a network request to the real-time service and get the ranking results back from the prediction service. Okay, but there are still problems in this diagram. What is it? Currently, all our data and the features are stored in offline data stores. There's no way this real-time prediction service can leverage the data. So what we need to do is to add another Cassandra service, a Cassandra key value store to acting as an online feature store. So it has two data sources here. You can basically get the real-time features either from our streaming platform by using the Kafka topic and transform the Kafka topic to your feature set, or you can actually have some sort of scheduled job to disperse your global feature from Hive feature store into your Cassandra feature store. So that's basically, there are so many different other ways to do it, but that's the approach we are taking right now. So similarly to the batch model, you also need to add some monitor to give you confidence of your model, how it actually performs in the production. Okay, so far, I hope you guys have an overview on the architecture of the AI platform in the UberEats. And now I'm just going to each component in more details. So in the feature generation steps, the step is very easy and straightforward because most of our data is actually tabular data, and all we need to do is write SQL queries, and the SQL queries will basically generate the feature set for you. And as you may notice, you don't need to write any single Spark program at all. So the other thing we do is we basically also use our little domain-specific language. So this allows you to reference specific features from different data source. So to reuse a lot of the features you curated in the Hive feature store, as we mentioned before. Okay, here. Let's see what kind of models we are actually supporting right now. So we're actually supporting most supervised learning models, and the unsupervised learning models we currently only support k-means. So for the training set, the first thing you need to do is to specify your data. And in order to specify your data size, you can basically pick how big your data range and you want to pick from. You can say, okay, I want to run a couple weeks of a training data set, et cetera, et cetera. And the other thing is you can specify a set of hyperparameters you want to configure on, and then the platform can automatically search the candidates of the hyperparameters for you and pick the best model. So for the cross-validation strategies, we basically just use a very straightforward holdout strategy, and you can also customize your own holdout policy. Okay, so the next thing we will do, basically, you can also manipulate the training process, basically is trying to specify how many Spark executors you want to run and how big each executor's memory is. And so in this way, you can have some sort of control how fast you want to get your training process finished. So if you remember the life cycle, so after you train the model, you basically want to analyze and compare your model with your current existing models, and the performance metrics we are using is very straightforward. So for binary, we use the area on the curve, and for the regression, we basically use the mean square errors. And so when the model is deployed in the productions, it's better not flying in the dark. And the proper way, monitor is very, very encouraged in this case, and it always gives you a better insight about how your model actually perform in the production rather than just in the test data sets. So looking forward, so what do we want to do actually to improve our platform? So the first thing we want to do is to add automatic feature generation. What do I mean by automatic feature generation is we can add multiple different UDFs, such as one-hot encoding, to actually make the feature transformation and the extraction like more automatic. The other way is to find out the better way to find the best configuration for your model's hyperparameters. Currently, it's still semi-manual. You need to specify the candidates of parameters you need to search on, but later we should have better algorithms to help you to make a better configurations. And the last is to provide more support on unstructured data rather than just tabular data. So with that, I'm handing over to my co-speaker, Xing. Thank you.
Is it on? Test. All right. Okay, thanks, Chen. So the next thing is we talk about some of the AI problems at UberEats. So interesting thing is when I decided to join Uber like a year ago, and some of my friends asked me, right, so are there any like real AI problems at UberEats? Because UberEats is just a food delivery app. How could there be any like AI problem for UberEats? And hopefully after today's talk, can give you a overview, at least a big picture of like all type of like AI problems we are facing at UberEats, and hopefully you will get a rough idea about like those type of work we have been doing at UberEats. So let's start with like the mission like for UberEats. So our mission at UberEats is basically want to make sure like UberEats, this app can make anyone to find their favorite food at any time. Doesn't matter. It's either late in the evening, in the midnight, it's during the weekday or weekends. Just want to make sure that UberEats just can make the eating well after this, right? At any time, like just for everyone. And to understand how we achieve this mission, then one way to think about UberEats is think about UberEats as a marketplace, right? Uber as a marketplace means that there are at least 3 parties take part in this marketplace. They are eaters, so I will have eaters who can order food from the restaurant. right? The restaurant will also receive orders from eaters. And also, like after the restaurant received order, they prepare a meal, and when the meal is ready, they will like notify the courier, right? Our courier partners will come and pick up the food and finally deliver the food to our customer, to our eater. Right? So given such a very dynamic marketplace in our UberEats, we need sophisticated algorithm to make sure everything is played in their role like in a consistent way. And in order to support such type of dynamic marketplace, AI basically is like the fundamental engine that is running this whole marketplace. To give you some examples, right? So between the, we have some very traditional like AI or machine learning problems, such as ranking and recommendation. For our eaters, for example, when eater open their like app, we need to give them a list of stores they may want to order from. Right? This is a very traditional ML problem. And of course, we have search. For example, some users, when they open like UberEats app, they already have something in mind. They know what they're going to order, so we need to provide a way for them to search, right? To get to find the right food or right restaurant they're looking for. And of course, we need to make sure that in the marketplace, highly dynamic marketplace, we need to do a good job in terms of like demand and supply like prediction or forecasting. For example, we need to like notify the restaurant owners what type, for example, when will be the peak hour, right? What will be the next meal you want to prepare even before like eaters place their order in order to get the restaurant owner like prepared. And between the restaurant owners and couriers, we have a few things that's also going on that needs AI support. For example, in order to minimize the waiting time for the courier, because the courier sometimes they don't have order in their car, they have to wait until some restaurant owners notify them like the food ready, can pick up the food, right? We need to have a way to position the couriers in a proximal location to some restaurant we have predicted to have like order, for example, in the next 5 minutes, in order to minimize like waiting time for our couriers. And also, like, of course, you know, at Uber, so sometimes we also do something we call cross-dispatch, meaning that a courier for UberEats can also be a driver of Uber. So sometimes, given when a restaurant's like meal is ready, we need to decide which courier or which driver we want to dispatch to get the order. In order to do that, the goal is to also create a more stable, consistent network. We don't want to, for example, we don't want, for some of like in the center of the city, we don't have like too many like couriers there that get like, they don't have a lot of like order because there are so many couriers. And for some place like near the boundary of the city, we don't have enough couriers. So we need to have some algorithm automatically dispatch like the right courier to the right restaurant. And of course, batching in our case, when we say batching, we mean, for example, we want to batch as many orders as possible for a given courier. For example, the worst case is for each of the like eaters order, we have a dedicated courier for that particular order. But that will be a huge waste of our resource. So a smarter way to do it is we figure out some orders that are going to the similar direction. So we'll batch those orders for one courier, and that courier may like deliver like 5 orders at the same time. That greatly minimize our cost. And even between the eaters and the couriers, we have a few problems. The first one is something, if you use UberEats, you must be familiar with it. This is the estimated time to deliver. This is also extremely hard problem, and this is also a problem we receive a lot of complaints, a lot of tickets. People just say like, our estimated time to deliver is not just not accurate. But unfortunately, maybe I will not be able to dive into this particular topic, but if you're interested, feel free to reach out to me, and we can chat offline about why this is actually a very difficult problem to have accurate estimate on the time to deliver of your food. And the second problem is dynamic pricing, right? Dynamic pricing meaning that, for example, when the user order food, the fee they pay for is not just the food, right? Also need to pay for the booking fee. Booking fee, you can think of it as similar to the delivery fee. You can think like, for example, during the rush hour, we don't have enough supply, then the price may go higher. Also, our delivery fee also depends on the delivery radius. For example, if you deliver some food to like 10 miles away, it must be more expensive than you deliver food to like 1 block away, right? And lastly but not least is intelligent spending. Actually, this is, I would say, most critical part for the success of UberEats. As you know, many people know, actually, Uber is still, I would say, losing money every year. And because most of the money actually goes to promotions, right? If you use UberEats, you know there are a lot of like promotion going on. You get a lot of coupons and discounts. And how to spend, for example, let's say we have a fixed budget. We have the fixed like money, and how do we intelligently decide which area are we going to spend our money, where to spend our money? It's either like to have some compensate for our couriers or want to give some promotion to the eaters. So how do you decide the algorithm that can directly can maximize the return on investment will be a key problem for our intelligent spending. Okay, that's a rough big picture about the AI problems we are facing at UberEats. And in today's talk, given the time constraint, I will not be able to dive into each one of them, right, to give you a better sense of what's going on. So here today we will pick 2 topics going to present today. One is also 2 topics that I guess is more familiar with the audience here, because those problems, you will see the similar problem in many other companies like Facebook or LinkedIn, right? And those 2 problems, basically one thing is a ranking problem, ranking and recommendation, and the other is search. And given the time, maybe I'll talk more about ranking and recommendation, first topic. If we have enough time, I'll also dive deep into the search. It depends on how the time works. For the ranking and recommendation is the fundamental problem for UberEats, because every time when you open UberEats, so on the right side is what you see when you open the UberEats, right? We have a list of restaurants. Some of them are grouped by some logic. For example, restaurant under 30 minutes. Some restaurant of certain cuisine. For example, top picks for Italian food, top picks for Thai food, and we also have something very similar to Netflix, I would say, is after you order something, we will guess because you order from this restaurant, some restaurant you may be also interested in. So we have such few problems. But I don't want to talk about a recommendation and ranking in general, because there are so many other different companies that are doing the same problem. So in this talk, I want to highlight a few things that are kind of unique to UberEats. Right. The first thing is, as we mentioned, UberEats. You can think of UberEats as a marketplace. So the first thing we want to talk about is how to rank in the marketplace. This is very unique because Facebook doesn't have a marketplace, LinkedIn doesn't have a marketplace, Netflix doesn't have a marketplace. Right? How to rank in the marketplace and what type of unique challenges will come up when you are doing a ranking and recommendation in the marketplace. Right? Also talk about how to build a fair marketplace. Right? When you do ranking, very few people talking about how to build a fair recommender system. People are talking about we want to build a relevant recommender system, but we care more about how to build a fair marketplace. The first one is the ranking to serve a marketplace. So here we will just dive a little deeper into the topic, be a little bit more concrete. But let's first talk about what is conventional AI machine learning model is commonly used for the recommender system for ranking, right? People use machine learning model. You think of machine learning model, you think of for example, GPT tree or the rank SVM or XGBoost or any type of algorithm supported by Spark ML Lib. So all those type of algorithms, we call it single objective models, meaning that there's only one type of label. Either you are going to maximize the click-through rate or something else. There's only one label. So in our case, this has put some limitations, because if we use such type of single objective function of type of model, we can either keep the user happy or keep the restaurant happy, because there's only one objective we can optimize on. And that comes to something unique about UberEats. So we focus, although so our solution is multi-object optimization, although our multi-optimization is already a very well-studied problem in the literature, but this type of algorithm play a very important role for UberEats. The reason is very simple, right? This is a marketplace. The eaters are as important as our restaurant owners. We need to pay equal emphasis to both parties, meaning that we have different objectives to optimize in our ranking and recommender system. And the multi-object optimization provides us a way to keep both the user happy and our restaurant owner happy. The next is one slide, quick slides. I don't want to go into the technical detail here. So technical detail here is just what is a multi-object optimization? It's very simple. It's more giving this is just a mathematical formulation. It's more for each of the fx, it's one objective, right? For example, it's either in our case, for Uber, we care about conversion rate. Conversion means when a user actually orders from a restaurant, right? We also care about, we want to minimize the restaurant churn rate. We don't want the restaurant owner to leave us. We want to keep them on our platform. We want to do both. For example, in that case, we have multiple objective or multiple models. For example, we have in this particular case on the right side of the plot, there are two in this particular case, we have two objectives. One is, like I mentioned, is the conversion rate, which is what we care about for the eater. The other is like the restaurant churn rate, which we care about. We want to keep our restaurant owners on the platform. In this case, both of the functions will be modeled by a single machine learning model, and we use Mu as a framework, as an optimization problem to figure out the optimal configuration given those learned models. And so I'm kind of like a little bit hands waving here, but the idea is, but I want to mention one challenge here. The challenge is not the machine learning model. I don't want to go to detail about machine learning model because everyone knows how to build a logic regression. Everyone knows how to build a GPT tree model. But the challenge here is how do you build how to formulate the multi-objective optimization framework in such a way it's solvable. For example, in a convex fashion, you want to find a convex optimization problem that can be solved. In this, I'll give one concrete example on how we utilize to solve the very classic dilemma in recommender system, which is a trade-off between relevance and diversity, right? UberEats, this is also a very important problem. For example, some users, the first time they open the UberEats app, for example, they ordered Italian food, for example, pizza, right? Probably because the estimated delivery time is short. For example, they can get the food in 5 minutes. But because that user is kind of new user, we don't have too much data, we may think that user loves Italian food or pizza, right? The next time the users main feed, right? The restaurant we recommend to user may be just everything is Italian, everything is pizza, so which might not be the best user experience. In this case, we want to find the right trade-off between relevance. We want to still make sure the restaurant recommended to the user are still relevant to the user taste. At the same time, we want to be more diverse in terms of the recommended restaurants. And this problem fits naturally into our multi-objective optimization framework because there are two objectives. One is relevance, one is diversity, right? In this particular case, then this diagram on the bottom just shows how actually on the high level, how do we tackle this problem? In this case, first of all, we need to still build machine learning models. It doesn't matter which machine learning we choose, but just a machine learning model for relevance and a machine learning model for our diversity. And we formulate this problem into a quadratic programming problem, meaning that we want to maximize the conversion rate, still maintain subject to some constraint. The constraint will be the diversity, right? Giving the session of the restaurant we're showing to the user. And we solve this problem and finally get the final ranking. So that's the main problem. That's one of the first problem we mentioned that summarize is how to optimize multiple objectives within a marketplace. We want to keep the couriers happy, we want to keep the restaurant owners happy, we want to keep the eaters happy. How do we do that? After this talk, you will get a rough sense like UberEats is using multi-objective optimization, this classic problem in optimization to tackle this problem. And the next problem I want to mention is how to build a fair marketplace. I want to be fair. So one of the concrete example is on UberEats, we have many different type of restaurants. We have some grand opening restaurant. It's either a new restaurant or a restaurant just get onboarded to Uber and UberEats. And we also have some very popular, very well-established restaurants. For example, so by the way, some interesting side story is those two stores are the two most popular stores on UberEats. One is Hello Guys. The other is Shanghai Dumpling King. So by the way, this is actually the most popular restaurant according to UberEats on San Francisco. It would be interesting if you can just, after this talk, because it's already lunchtime, feel free to use the UberEats, right? To order food from Shanghai Dumpling King or Hello Guys and try it out and see how it goes. Those are very well recommended restaurants for everyone. Yeah, so let's come back to our topic. So the problem is we want to keep this fair. For example, so what's the problem would this be, right? On our UberEats platform, those very well-established restaurants, they'll tend to get more orders. In our algorithm, actually will pick that up. Our algorithm will display those popular restaurants to a high position in our main feed to the user. So basically, this is a rich get richer problem. And for those low volume restaurant or new restaurant, they may not get enough orders. And this may be a big problem for us because some of the restaurants there, that's local business, people's income depends on it, right? We also need to make sure it's fair so those restaurant owners will still stay on UberEats. So the algorithm we use is still a very well-studied algorithm or framework in machine learning or AI. It's Multiarmed Bandit. I guess many folks, I don't know whether you have heard of Multiarmed Bandit, this type of algorithm before, but the basic idea is this is a very well-used framework for the exploit, meaning that In this case, explore, meaning that we want to explore like a new restaurant, things we are not sure, things with high uncertainty. Exploit, meaning that we want to still recommending those like very popular restaurants to a user, for example, Shanghai Dumpling King. We know for sure the user is going to love it, so we're still going to try it out, to recommend this to a user. And this part is, I know maybe we don't have time to dive deep into detail about what this part is, but this one just saying like, we need to give some of the no volume restaurant a second chance. Sometimes they may do good actually if we give them enough chance. Give chance meaning that we want to display them more to the user and get them to order from the user. So that's two main problems for the feed or the recommendation problem, and since we don't have enough time, so I'll very quickly go through like the search, right? For search, we also have a very diverse set of different machine learning problems. So here are a few like challenges we have. Let's quickly go through. First one is, when we UberEats, right? If you are going to build a recommender system, you need to understand the items. In our case, each item is either a restaurant or a food, so we need to understand our food. Either, for example, we need to understand if a query is a restaurant, is a dish type, or is a cuisine type. For example, there's a very famous Thai restaurant called White Elephant, right, in San Francisco. Right? When the user type in White Elephant on UberEats, we need to understand this is not an animal. This is actually a restaurant. And if this restaurant is not available on UberEats, we need to understand this restaurant is a Thai restaurant. So maybe we cannot return White Elephant, this restaurant, to the user. We may return some Thai restaurant. Maybe that will give the user a better experience. And we have some other manual results because UberEats is still new. Most of the like popular, like well-known stores or restaurants have not been onboarded to UberEats yet, right? So a lot of times, for example, one of our most popular but unfulfilled query is Chipotle. People search for Chipotle a lot. People love Chipotle a lot based on our data in San Francisco. But unfortunately, Chipotle is currently not UberEats yet. But so what will happen, like if the user for Chipotle, we have two choices. We can either say there's nothing returned, or we can return something similar to Chipotle. Right? This is also a challenge we're going to handle. And of course, the ranking is like we still have ranking problem in search. But ranking, the main challenge is personalization. Do we want to do personalization or not? Actually, in ranking, for recommender system, the answer is pretty straightforward. We want to do personalization. Right? Personalization is good for ranking our recommender system. But is this personalization good for search or not? This is a question. For example, we know for sure a user loves, for example, Thai food. But users happen to search, for example, American food. Do we want to blend any like Thai food into the return result? May or may not. Right? So this is also a very challenging problem. We want to do some certain degree of personalization, but not too much. Right, so a few solutions, I'll highlight some of the solutions we have. We don't have time to go through each of them. The first one is a very hot topic. I mean, the first two actually, both of them are very hot like buzzwords in these days, right? The first one is representation learning. If people think of representation learning, basically the deep learning or like the word-to-vec or dog-to-vec, sec-to-sec, those type of like machine learning, like deep learning models. And also for how to understand our food, we need our knowledge graph, right? Google, they build a knowledge graph for their search engine. In our case, we also have a search engine. We need to build our food graph, right? We need to understand our food. Quickly go through them. So for food graph, like I mentioned, for Chipotle, right? We need to understand, is this a restaurant? Is it fast food? Does it sell tacos? For example, we don't have Chipotle. Can we recommend other like fast food chain restaurant? Can we recommend some other restaurant that sell good tacos or burritos? And for poke, right? Poke is also a very, I would say, uprising top cuisines on UberEats. And there are not too many like restaurants serving poke, but poke surprisingly is very surprising. It became more and more popular in San Francisco. More and more people are searching for poke. If you don't know what it is, poke is basically a Hawaiian style, or similar to like maybe like also Japanese type of food, raw fish, similar to sushi. It's very good. Currently there are a few like good poke restaurants on UberEats. Feel free to try it out. And the representation learning, I don't need to go through this slide. Everyone maybe, if you keep an eye on the recent advancement in deep learning, you will get a rough idea what is representation learning. In our case, our representation comes from two parts. The first one is based on a knowledge graph. Right? Second one is based on more traditional, for example, deep learning techniques. Right? We have the word-to-vec and we have the graph type of algorithm, and we also have trained our like end-to-end deep learning network in order to learn representation of our food, our cuisine, our dish type, our restaurants. And finally, it's like a ranking problem. A ranking problem, I mentioned the key dynamic challenge is how much do we want to do personalization, right? We don't want to over-personalize, but we still want to make sure the users, if a user search for something, like different users with very different tastes, their return result will be slightly different. Okay, takeaways. We have don't have time. The first thing is UberEats is a next time if you think of UberEats, you can think of UberEats as a marketplace. Right? We have the eaters, we have restaurant owners, and we have our courier partners. And AI is underlying engine that runs this marketplace. And last but not least, we are hiring rock stars in AI. Please take a look at our job page or reach out to me or Chen if you are interested in our UberEats problems. All right, thank you very much, and bon appetit, it's lunchtime.
So you said that you're using Word2Vec and also the food graph. Why do you need both of them?
What's up?
I think the way that you're using them, it's kind of similar. So between food graph and Word2Vec, like what's the differences between how you're using it?
So food graph is something, for example, we can digest some of the external data source, for example, Foursquare or Wikidata, right? Those data like is on the observed space because we know, for example, Chipotle is fast food chain restaurant, right? The Word2Vec is mostly based on, for example, either based on menu description, we want to project those items into a latent space. Right? The main difference I would say is one is on the observed space, one is on the latent space.
Okay, so you manually create the food graph?
We build our food graph by digesting or ingesting different type of data sources. For example, like I mentioned, like Foursquare or Wikidata.
Okay, and then for the Word2Vec, how do you train the Word2Vec? Like what kind of text did you feed it?
So Word2Vec, actually, we use a generalized version of Word2Vec, meaning that we have two types of Word2Vec. One is like very traditional one, is basically just called TensorFlow, right? Just run on the menu descriptions of each dish, right? The menu description is text words, right? It's words, literally words. So it fits naturally into Word2Vec. Another thing is Word2Vec, we generalize into a different scenario where each of our, we can talk about that later, but each of our word, in this case, is actually order. So it's a state activity-based Word2Vec. But I'm new to be hand-waving here, but basically, we're using one traditional way of doing Word2Vec, and one is more like based on activities.
Okay, so you use the pre-trained Word2Vec, and then you also trained your own Word2Vec.
We use our own trained Word2Vec. It's very simple. I just run an algorithm on our data. We have enough data. We just run it.
Okay. Yeah. All right. Thanks.
All right. Thank you very much.
Thanks. We got another one.
How do you combine the multi-armed bandit and the multi-objective optimization? Do you do the bandit only on the on one of the two or on both of them?
That's a good question. Actually, for Multiarmed Bandit, I didn't go to the detail, but if we go detail, it will be very clear. So we use upper confidence bound as one of our concrete examples to solve the no volume restaurant problem. But if you look at the upper confidence bound algorithm, it fits naturally into the MOVE framework, the multi-objective optimization framework. So actually, they are combined into a single big optimization problem. Yeah. By the way, thank you guys for staying late. I know it's already lunchtime.
So you mentioned your use of the multi-armed bandit.
Yes.
Are you using or exploring any more sophisticated sequential decision-making techniques, such as contextual bandits, or even more episodic techniques like classical, reinforcement-style algorithms?
That's a great question. So first of all, in this slide, what we're using are very naive. Basically, the upper confidence bound. Basically, we're using the variance of each item to do exploit it. Another thing we're using the multi-armed bandit, which is not context like MAB, is we use it for our A/B test. Right? You can think of basically we have different treatment groups. We use the multi-armed bandit to decide the traffic allocated to each of the treatment group. That's another way of using that. Basically, those are two main use cases of the MAB in UberEats.
So you're not currently doing things like using contextual bandits episodic techniques?
Actually, this one is, you can think of, depends how you define contextual multi-armed bandit. So my understanding of the contextual bandit is you use of some context information for your bandit problem. In our case, we're actually using the context information. For example, in our case, even the UCB, right, the upper confidence bound, we need to estimate like the mean and the variance. And the estimator of the mean actually uses contextual information. Basically, the mean is a model. The model, for example, is a tree model with some features. Those features are contextual features. So it's kind of like contextual multi-armed bandit.
Hi. Congrats. Well done.
I would like to know what are the key differences between UberEats and other online food delivery services?
That's a great question. So although that's kind of out of the scope of this talk, but I think Chen shared a thing here. So I think the key difference, actually, I think we are just, it not necessarily mean that Uber is better, but actually Uber is leverage, it's actually standing on the shoulder of a giant. The giant is Uber. Right? For example, we have almost unlimited couriers waiting there to deliver the food because we can leverage Uber. A Uber driver can also be a Uber Eats courier. So in that part, we almost never worry about whether we're short on, for example, couriers. I think the one biggest advantage. Another thing is, I feel like the difference is, I would say we have better recommender system, but yeah.
Can I ask one question as regarding to how you build this food graph? Is it manual based or is it more like an auto way to build the the food graph?
So food graph here is actually we are not building everything from scratch. We're still leveraging what is already available out there. For example, actually we have it. So I have a very close. Uber have very close collaboration with Foursquare. Right? Foursquare already have a very sophisticated food graph already. So actually we used a lot of their data to help us bootstrap our food graph. And also we also digest something from the wiki data. Wiki data we also, for example, for different type of cuisine, like sub-cuisine, dish type. So basically we're using the information outside of Uber Eats to build our Eats graph.
So how you update this graph? Because I assume this one is ontology, right? It's kind of ontology based. So how are you going to update this kind of food graph? If let's say there's a new merchants coming on board in your platform?
So currently, frankly speaking, we don't really update the graph. We're still in the stage of adding more components into the graph because currently our graph is still very limited. So we're still on the stage where we don't really care about whether the graph is outdated or not. It's more like we're ingesting different data sources we can find available to this to construct a big graph. But we haven't gone there how to keep your graph always updated. But one thing is we kind of feel different from Google, for restaurants, for those type of information kind of static. Right? For example, restaurant, they don't really change their cuisine type. Right? But anyway, yeah.
Thanks. Any more questions? All right, thanks
All right,
again
thank you
for
very
your
much. Thanks,
fascinating
everyone.
presentation.